All right. All right. So today we're going to talk about the exam, and well, I'm going to spend a whole lot of time on it. I'll post the solutions to the exam in the next day or so. I already scanned it. I just need to post it on the web. I'll do it when I post your notes and stuff later. Here's the way the exam works. Let me just write it down. I had originally told everyone that the way I was going to do it is that problems 1 through 9 were 20 points apiece, and then number 10, A, B, or C, you had to do 2 of those, right? That those were 30 points apiece. So you would have got here, 180 out of this possible, and out of this 60, right? Which means total of 240 points were possible. I just decided when I was grading it to cut all those in half. Okay, so instead of 20s for 1 through 9, it was 10. And that made this 90. And then here, instead of 30 points apiece, 15 apiece, that was 30. That means there was 120 points possible. And so I graded your test out of 100 points. So you could have gotten 120 on this test. That was the highest you could get, was 100, and it would be 120, not 120 out of 120. It would be 120. So there was a 20-point curve to the test, if you want to look at it that way. Okay. I think the highest grade was a 108, then a 103, something like that. So what I'll do is I'll call your name. On your test, when you get it back, you'll see your test, and on the top right-hand corner, you should have a couple. I'm just going to make these numbers up. 63, 72, then it'll say something like, I don't know, 97, 82, and it'll say B and C, something like that. The top number is the grade on this exam. The second number is your grade in the class. And then whatever numbers next are what you need to average the rest of the way for those grades. So like this student got a 63 on this test, has a 72 in the class, would need to maintain a 97 average for a B in the class, would need an 82 for a C, and an A is not possible. So if an A isn't up there, it means it's not possible. Okay? Questions on that? All right, Michael, I graded yours already. Abby? We need to talk, Abby. It's nothing bad, but I need to talk to you, okay? Crystal, Cody, Jeff, Frank S., Elias, Katie, Jacob, Jasmine, Daniel, Perez, Courtney, Kyle. Courtney, I don't think I put the letters next to the numbers for you. You know, like what you need for a B, C, A. So if you're confused about it, let me know. Myra, John Buchanan. Same with you, John. I didn't put the letters next to it. I'm sorry. I can straighten that out later. And Caitlin, I didn't do yours either. Caitlin and Daniel, I didn't do yours either. So it's like grade on this, overall grade, A, B, C. Okay? Or no, other way around. CVA. Okay, so for you, this is your grade on this test, overall grade, what you need for a C, a B, and an A. Okay? All right, now here's what I did. I sent an email out on Frank. I called you. I did. I looked at you too, and I was like, maybe he changed his name. Okay. Listen, this is very important what I'm about to tell you, okay? Wednesday I graded these. Thursday was the last day to drop the class. I sent out an email saying, here, go check your grade, right? I posted the grades online. If you cannot mathematically pass the class, you should consider dropping the class, right? Then I went to go drop a few students who requested to be dropped, and I looked at all the grades, and I kind of took the initiative to drop students who couldn't mathematically pass anymore. Now, the reason I did this is because it's easier for me to drop someone and reinstate them than it is for someone to not drop and then try and drop after the drop date. So let's say I withdrew you, because some people in here might have been withdrawn, they don't even know it. Then if we talk about your grade, and maybe there's a way mathematically we can figure out a way, I drop a quiz or something, you can still pass. It's easier for me to put you back in the class than it would be for me to have not dropped you, and then you're like, hey, I really wish I would have been able to drop and not been able to. Now you can't. Does that make sense? So after class, please go check to see if you're still in the class, all right? And if you're not and you want to be in here still, we need to talk, okay? Yes? All right. That's the first time I've ever done that, so that's why I'm kind of like, I don't know how it's going to work. What's that? Well, it's not something that I can just do, but I have to fill out paperwork, but I can do it. Yeah, once the drop date's passed, I can't, no one's going to be able to drop you. So I kind of made the call on that. All right. I also sent an email with the homework for today. I'm just kidding. I'm just kidding.
I was looking.
But no, I didn't. I gave you the weekend off to not think about math for a while, or get caught up, whatever it may be. But I did ask you to do that quiz. I said that you would have that. You have to use some technology, perhaps, to solve that second problem. Remember what I'm talking about? So I will collect that now. It was that take-home quiz, 2 problems. One had to do with finding the absolute max and min. The other one had to do with verifying the mean value theorem. Thank you. Did you try and get an answer somehow?
Well, I didn't get around to it.
Okay, but you have the equation that you would have had to have solved. Okay, that's something.
Use some technology, and I was like, okay.
I wanted to see what people would do.
I forgot to finish it.
Okay, well, better than nothing, right?
Yeah.
Okay. Myra, I've got your test here. Don't go too far. No, Myra. Here we go. Myra, your test is up here when you're ready for it. All right, thank you. Right here. Oh, we can talk later. Let me, yeah. All right, we are going to, if you have any questions on your test or anything like that, please just bring it to me after class. All right, so I did not ask you to do anything at home, but maybe you did watch the video for 4.3. If you did, great. If you didn't, you should be able to get by here. We're going to move out of section 4.1 and 4.2. That's the last thing we cover for the test. 4.3 talks about the derivative and how the derivative affects the shape of a graph. And this section, the next one, the next three sections we're going to do today are all kind of connected, all right? So if you have any questions as I'm going through this, please ask. The first note here has to do with the first derivative. So remember, the derivative is just the slope of the tangent line, right? Yes, everyone? Okay. Derivative is the slope of the tangent line. So if our slope is positive, right? If our slope is a positive number, that should mean that our function is increasing. So look at this blue function here and look at the tangent line at all those points. So the green dot's moving across the function. Notice that the derivative, the slope of the tangent line is always positive. So if the slope's positive, that means your function must be going up as you move from left to right. That makes sense? Positive slope means your function's increasing. Now, negative slope, so if your derivative is negative, this should be backwards. That's a typo. If your derivative is negative, then your function must be going down as you move from left to right. Does that make sense? All right. And then, of course, if your derivative is 0, then it's flat the whole time. Then your function must be constant. So it's just a flat line. And that's what that first note in this section says. If the derivative is positive on some interval AB, then f is said to be increasing on that interval. If the derivative is negative on an interval, then it's said to be decreasing. And if it's 0 on an interval, then it's constant. So this tells us that we can look at a derivative and tell a lot about the function. Here's an example of a function where it switches. So as I move from left to right, I'm going up right now, right? I'm increasing, and my derivative is positive, right? And I have the line is green. When I get to the top, my derivative is 0, isn't it? Flat line, turned purple. And then once I go past this, my derivative is negative, which means I should be going down on the function. Until I get to the bottom, it'll flatten out again. Derivative is 0, and then the derivative will be positive again. All right, with all of that said, we have what's called the first derivative test. The first derivative test says, suppose C is a critical number of a continuous function. What does it mean to be a critical number of a continuous function? What happens at a critical number of a function? Either what? What's 0? The tangent line has a slope of 0. The derivative is 0, right? So to be a critical number means the derivative is 0 there, right? Or what? There was another thing we checked for. Does not exist. So the derivative doesn't exist there. So this is saying if you get some value C, like let's say 2, right? If you go to 2 on this function and the derivative is 0 there, or the derivative is undefined there or doesn't exist there, then there's this check you can do. If the derivative changes from positive to negative at that point, then we have a local maximum. If the derivative changes from negative to positive, then we have a local minimum. And if it doesn't change at all, we don't have a local maximum or a local minimum. So let's try and figure out what that means by looking at this here. All right, is it clear to everyone that where my arrow is right now is a local maximum? It's the highest point on that graph locally. So if I move my slider around, right now, to the left of that point, what's my derivative? Positive. To the right of that point, what's my derivative? Negative. At that point, what's my derivative? 0. So I have a critical number at 2, don't I? Right there? Wait, is it not 2? It's not 2, is it? What value is that? Oh, it's some crazy number. Never mind. So it's some x value. I don't know what it is, somewhere in here. If I go up to that, my derivative there is 0. To the left of it, my derivative is positive. To the right of it, my derivative is negative. So according to the first derivative test, if it changes from positive to negative, that means moving left to right from positive to negative, we have a local maximum. Does that make sense? You go up and then you come down, so it has to be a maximum. Now, let's look at what's happening in the middle here. As I move across here, my derivative is negative, and doesn't it flatten out to 0? Which means we have a critical number, don't we? So to the left of it, it's negative. To the right of it, what's it going to be? Negative still. So what happens if we have a critical number? To the left, it's negative. To the right, it's negative. What does that tell us? If it doesn't change signs, it goes from negative to negative, then there is no maximum or minimum. Does that kind of make sense or not? It's kind of like you were going down, you flattened down, then you kept going down. Well, that's not going to be the highest or lowest point. You would either have to go up, then down, or down, then up. Now, at this last point on this curve, my derivative is negative, right? And then I get to a point where my derivative is 0. That's going to be right there. So that's my critical number. To the left of it, I was negative. To the right, I was what? Positive. Okay. So at the end of this all, I labeled the green part of the graph is where I'm increasing, the red is where I'm decreasing. I have a maximum here, minimum there. No maximum in there, and then a minimum. Yay? Nay? That's okay? All right. All right, now we have another test, and this comes from the second derivative. So what does the first derivative tell you? Tangent, but as far as like positive and negative, what does that tell you? If the derivative is positive, that means you're increasing, and then if it's negative, you're decreasing. So the first derivative tells us where our function's going up and down, right? Just where the function goes up and down. The second derivative also tells us something. It tells us about what's called the concavity. So I want to look at that same graph we just looked at, okay? And I'm having the computer calculate the second derivative at each of those points. So imagine taking the derivative 2 times and then plugging in the x value. Right now, my second derivative is negative, isn't it? And then it's still negative, and still negative. And then it becomes positive right there. And then it's still positive, then it's negative, then it's positive, and it stays positive. So what the hell is the second derivative telling us? It's not telling us where it goes up and down, does it? It's something else. Concave. How do you mean concave? I mean, a smile or a frown. That's what it's all about, okay? Look at the red part of this graph. Doesn't the red part of this graph look like part of a frown? Like, like a smiley face, someone's frowning? Sad face? Did I say smiley face? Okay. Frowning. Okay, a frown, right? Someone's sad face, right? Down. And then this green part is like the left side of a smile, right? If we were looking at a smiley face, that's like the left side. And then here's like the right side of a frown. And then this looks like left side of a smile and then the right side of a smile. See that? You don't see it? If you don't, tell me. Look. That's concave up. That's concave down. All right? This would mean the second derivative is positive because it looks like a smile. This looks like a frown, right? Back to my picture. This red part looks like a frown. Now, it's not the whole frown, right? It's just part of it. But this right here is where the frown becomes part of a smiley face. And then the smiley face becomes part of a frown. And then the frown becomes part of a smiley face. Do you see that now or no? Frank, I was looking at you because you shook your head. You sure? All right. Anyone else? Now, mathematically speaking, we don't talk about smiles and frowns. It's something else. And it's not many people see it right away. Does anyone see the difference between what's happening here and what's happening over here? I mean, other than the smile and frown. I'll give you a hint, unless someone sees it. The tangent line. Okay. Yeah, right here in the green, isn't my tangent line below the curve? It's below the curve, right? That tangent line is underneath that curve. But when I move it over here, isn't my tangent line above the curve? That's the true definition of concavity. Anywhere your tangent line is above the function is where you're concave down. Anywhere your tangent line is below the function, you're concave up. So if I go back to my picture over here, if I pick any point on a smile and draw a tangent line, my tangent line's below the smile, right? It's touching at one point, and every point around it should be above that. And then if I go to my frown, my tangent line is above it. I mean, it touches at one point, but the rest of the line is above it. So that's the true meaning of concavity. So I'll go back up to the definition. If a function f lies above all of its tangent lines on an interval, so the function is above the tangent, then it's concave up. So you've got your smile, and you've got your tangent lines below it, right? Function is above the tangent line. If it's the other way around, the function f lies below all of its tangents, then it's concave down. That's called an inflection point. So look at this right here. If the second derivative is positive on an interval, we say it's concave up. That's easy to remember, I think. Second derivative positive means you have a smile, right? Positive people smile, for the most part. If the second derivative is negative, then it's a frown. So negative people are always grumpy, right? They're always frowning, so you've got a frown. Anywhere that you have a place where you change concavity, it's called an inflection point. So here you can move this out of here. You can switch. Here's the first switching concavity right here. Here we're frowning, concave down, and then right there is where we make the switch. Concave up, concave up. So there's our first inflection point. Here's our second inflection point, and here's our third inflection point. Okay? Questions on that? All right, second derivative test. So what was the first derivative test? It said if you have a critical number, right? And then it switches, the first derivative switches from positive to negative, you have a what there? First derivative test. You have a locomax, right? If you have the first derivative is a critical number, you have a critical number, right? First derivative changes from negative to positive, you have a what? Locomin. Second derivative test is a little bit different. Check out what second derivative test says. Suppose the second derivative is continuous. All right, so you take the second derivative, it's a nice function. If the first derivative is 0 at that point, what does that mean? Graphically, first derivative being 0 means what would we have there? Flat tangent line, right? Flat tangent line. If you have a flat tangent line at a point and the second derivative is positive, then you have to have a local minimum there. Why? So let me try and illustrate this in steps. First of all, let me give you a point. Let's say that at that point, the first derivative is 0. So I have a flat tangent line, don't I? Then the second derivative is positive, which means I have to have a smile there. Can't you see that that can only be a local minimum? Right? That makes sense how that's constructed? If you look at the other way around, Oops, these are all already in here. Sorry about that. So here's a point. Let's say that the first derivative is 0 there. The second derivative is negative. I have to have a frown. That means that the function has to be, or that has to be a local max. So the second derivative is very powerful. It gives you a way to find whether or not you have a local max or min pretty quickly. The drawback to the second derivative test is that you have to take the second derivative. So sometimes taking the second derivative is hard, but it's a pretty convenient little test. Okay, that's it for that section. Let me do something here. Minimize this. Yes, this is calculus right here. We were talking about inflection point. I just want to show you something real quick. Like, why is inflection point important? Let's say that this is time and this is money. Let's say you have, well, you know what? Let's not use time. Let's say number of widgets produced. And let's say this is your income. And I'm just going to pick something, cell phones or, smartphones. Let's say my company makes smartphones, and that's what the widgets are. Okay, we'll just say a widget is a smartphone. I'll switch it. Smartphone. My company makes smartphones. And we produce so many per month. All right? And we make money off of those, don't we? Let's look at a graph of the income off those cell phones. What if my graph looks like this? Okay? Would you agree that the more cell phones I make, the more money I make? I'm always making money the more I produce? Do you agree with that? If I only produce this many, then I'm only going to make that much money. If I produce this many, I'll make more, right? But there's an important point on this graph, the inflection point. Okay? The inflection point is where the smile becomes the frown. It's probably somewhere in here. And in economics, in business, this is called the point of diminishing return. What it means is that if you look at the tangent line, like let's look at a tangent line over here. That tangent line's pretty steep, isn't it? Yes? But as I move past that, my tangent line is still positive, so I'm still making money, but that tangent line is not as steep as the one before it. And as I move on, I'm still making money, but I'm not making money as fast. So that green point represents the point at which I'm making the most, the fastest. Anything past that, I'm still making money, but not as quickly. That make sense? I'm just trying to show you an example of where the inflection point might be useful in a real-world application. You could also look at this instead of smartphones. You could look at something like horsepower and fuel octane or something like that. So you realize the higher the octane, the more horsepower you're going to get, but there's this critical place where you get the most bang for your fuel, right? Does that kind of make sense? Anything past that, yeah, you're still gaining, but it's not as fast as is at that one critical place. Not everything necessarily would. I mean, some graphs might be linear, in which case the more you put in, the more you get out. There's no point of diminishing return. I don't know. Yeah, I don't know. I mean, I'm just saying every model is different in the real world. If you take something as simple as, an exponential function that looks like this, that would have no point of diminishing return because it's always smiling. There is no change in concavity there. And a lot of things grow exponentially. So not everything would have a point of diminishing return. Okay. That was just get you kind of acquainted with the ideas here. Now what I'd like to do is I'm going to do, for the next about 20, 25 minutes, I'm going to do some examples out of the book from this section. And then you're going to take an in-class group 30-minute quiz. It's going to be a long quiz over this, okay? So I'm going to start off with the first problem here. And I'm doing number 1 right out of the book. The function is f of x equals 2x cubed plus 3x squared minus 36x. Now this is a very nice polynomial function, right? Part A of this says find intervals where f is increasing or decreasing. Part B says find local max, local min. And then part C, find intervals, I'm going to say INT, of concavity. And then find inflection points. I'm just going to put IP for inflection points. But local min, local max. Sorry, yeah, thank you. Now, I'm also going to point something out here because this is absolutely critical when we get to 4.5. Does everyone see that with this, what we're about to do, we're going to find local max and local min? On your test, weren't you asked to find absolute max and absolute min? Right, that was 4.1, wasn't it? What's the difference between what's happening here and what was happening in 4.1? There's something very different about the two problems. We have a second derivative here, yes? There's something else, a little more subtle. It's local, not absolute, right? The idea of increasing these, there's something that in this problem I didn't give you. An interval. An interval. See, if you look at a function and you close it off on an interval, it must have an absolute max and an absolute min, right? That's what 4.1 was about. So all we did was we figured out the critical numbers, we found the endpoints, and we plugged all those into the function, right? And we just compared them. Here, I give you no interval. So we're looking at the function on its entire domain and saying, hey, where are the high and low points, right? And where do you change concavity? So that's a huge difference. So I'm going to point out here in red, we're doing this on the implied domain. We're not doing it on an interval. Not on closed interval. That's a big deal, as we'll see later. All right, so how do we do part A? How do we find the intervals where the function is increasing and decreasing? Let's find the derivative, right? Okay, so part A, here we go. First thing I'll do is find the derivative. 6x squared plus 6x minus 36. The next thing I'm going to do is find the critical numbers. How do you find the critical numbers? We've done this, haven't we? All you have to ask yourself is two things. Where's the derivative 0? And where's the derivative not exist? Well, what about the does not exist? We don't have to worry about it, right? NA, not applicable. Why? Our derivative is a polynomial. Polynomial functions are defined everywhere. It has no issues. What about setting it to 0? So that's a quadratic equation. I'm just going to factor 6. Well, I'll divide everything by 6. How about that? Divide both sides by 6. And then factor x plus 3x minus 2. So your two answers are -3 and +2. And see, this time we don't have an interval, right? So we don't have to check to say, oh, do those numbers live in that interval? We're going to have to look at both of them. Yes. Did I what? Did I change it? Okay. Any questions up to this point? So I know where the critical numbers are, right? I know the places, these critical numbers right here, at x equals -3, and at x equals 2, my derivative is 0, which means we have a critical number, right? Now, the first derivative test said there it is right there. If the derivative changes from positive to negative at C, then it's a local max. If it changes from negative to positive, then it's a local min. If it doesn't change signs, it's nothing happens, right? No local max, local min. So watch the way I'm going to do this. Once I get to this point, and this is going to be our standard practice from here on out, I'm going to draw a number line. I'm going to label the 2 points on my number line. Just make sure you get them in order. And I'm going to use that to partition my number line into in this case, in this problem, into 3 separate regions, right? And then I'm going to pick test points. I'm going to pick a test point over here to the left of -3, a test point between -3 and 2, and a test point to the right of 2. So I'm going to pick a test point in each region. Now, the test point you pick can be any point you want as long as it is in that region. So I'll pick -4, I'll pick 0, and I'll pick 3. Is that all right? What am I interested in? What is it about? What am I going to do with these test points? I want to see if my function is going up or down over there, right? But the way to check if it's going up or down is to take those numbers and plug them into the derivative. Because the derivative is what tells you if you go up or down, right? If the derivative is positive, you're going up. If derivative is negative, you're going down. So what I'm going to do is I'm going to take f prime of -4 and figure out what it is. So everyone plug -4 into the first derivative. Remember, the first derivative was 6x squared plus 6x minus 36. So isn't that 6 times -4 squared plus 6 times -4 minus 36? And if you need a calculator, you probably want to get your calculator out because you'll need it for the quiz most likely. You get 36? Anyone else get 36? Yes? All I care about though is what? It's positive, right? It's positive. That's the key. Because it's positive, right? What does that tell me my function is doing over there at -4? My function, so watch the way I write this over here. My function is increasing over here. Why is it increasing? Because the derivative over here was positive, right? The derivative being positive means the function's going up over there. Now what's happening at -3? It's flattening out, right? So what should we check next? What? 0. The derivative at 0. And at 0, it should be an easy computation. It's negative 36, isn't it? Which is less than 0, which means we have a negative number. If the derivative is negative, what does that tell me about f? Not concave, we're at the first derivative. It's what? Decreasing. So my function went up and then it's coming down, right? And then let's plug in 3 into the derivative. Comes out to be positive? What's the number? What is it? 36 again? It's positive, and therefore, if my derivative is positive, then that means my function is going up over here. So this function goes up, then it comes down, and then it goes back up. It reaches its maximum point where? Where does it reach its max? At what x value? Negative 3, good. Where does it reach its minimum value? At 2. So I can actually answer, I think, parts A and B here at the same time. Right? Part A, where was the function going up? Where was it going down? So let me go back here. I'll put it in blue. For part A, f is going up on what intervals? Where's my function going up? To the left of negative 3, correct? So how do you say to the left of negative 3? Less than negative 3 or negative infinity to negative 3? Right? Interval notation. Is that the only place it's going up? No, it's also going up past 2. And anytime you have 2 intervals, you put a union symbol between them. How's that? And see my notation, F with the up arrow? Is everyone okay? I'm talking about this, F with the up arrow. Is everyone clear that that in this class is going to mean F is increasing? All right. Now, where is F decreasing? On what intervals? Negative 3 to 2. And that's it, right? Now, I'm going to answer part B above this. For part B, where's my local min and where's my local max? So let's talk about local min first. Where does it happen? At x equals 2, right? That's where it happens. That's where I have a local minimum. Remember, my graph is going down, then it has to go up, right? Over here, it was up, then down. So I should have a local minimum of x equals 2, but I would actually like to know what the minimum value is, what that local minimum is. So how would you figure out what the local minimum is? Plug it into the original function to figure out what the value of the function is there. So plug 2 into the original function. I'm getting negative 44. Anyone else? Okay. So you could, if you want, look at this as a point. The point 2, negative 44 is your local min. And then what about local max? Where is it happening? Negative 3 is the x value. And then plug that negative 3 into the function. Anyone get 81? Yeah, 81? Okay. Any questions? No? Sure. All right, I need to go to a new page here. All right, how about this? Part C. We want to know the intervals of concavity and want to know the inflection points. All we do for part C is exactly what we did for part B, or A and B, except we work on the second derivative, not the first derivative. So what would the second derivative be? Say it. 12x plus 6, that's it? Everyone agree with that? What I want to know again now is where's the second derivative equals 0 and where's the second derivative not exist? Well, as before, the second derivative not existing we don't have to worry about because it's nice. The second derivative being 0 is a linear equation. I don't know why I put 16. That is x equals what? 1/2? Negative 1/2, thank you. Seeing if y'all are awake or not. So I have to write things down incorrectly to get y'all to respond. That'll work. We can do that. What now? If we plug negative 1/2 back into the derivative, it'll give us 0, right? What did we do? What did we do with the previous problem? Once we figured out those numbers, what did I do? I did a number line. Okay, that's what we'll do again. Number line. I put negative 1/2 here. That's going to split my number line into 2 regions. And now I'm going to pick 2 test points. One to the left, one to the right. What's a good number to the left of negative 1/2? Negative 1? What's a good number to the right of negative 1/2? 0 or 1 or 2 or 3 or pi or e. Doesn't matter, any number, right? But try and pick something that you think is going to be easy to plug in. Now, where am I going to plug these in? Into the second derivative. Because remember, second derivative tells you if you're smiling or frowning. So what's the second derivative at negative 1? Well, that's 12 times negative 1 plus 6. That's negative 6. That's less than 0. Right? What does it mean if my second derivative is less than 0? What is my original function going to be doing there? What is it going to be doing? Not decreasing. Concave down. So it's frowning, isn't it? So I'm going to put a frown like this. If you even want, you could, put in a little face there. You don't have to, but it's an option. Now I'm going to test the second one. The second derivative at 0, plug in 0, you get 6. That's positive, right? What does that tell me? If the second derivative is positive, that tells me the original function is concave up. Happy, right? So, if you're taking anything away from this, the first derivative tells you where you go up and down. The second derivative tells you where you're smiling and frowning. That's it. So let's answer part C. For part C, where is f this? Now, I'm going to use that to mean concave up, everyone. All right? Instead of writing the words concave up. Where is f concave up? Where does it start? Negative 1/2 to forever, right? Where is the original function frowning? Negative infinity to negative 1/2, right? Where are there inflection points? There's only one, right? X equals -1/2. Now, as we did before, I'd like to now figure out, well, what's the function's value at -1/2? So go back and plug -1/2 into the original function. Original function, right? Anyone have it yet? Anyone have? Anyone? Anyone? What'd you get? -63/2? Anyone else got that? -17? Anyone else? I'm looking for 2 people to confirm the answer. Negative what? Please, not all at one time. Raise your hand. Where are we plugging this into? 2x cubed plus 3x squared, right? Okay, so 2 times -1/2 cubed plus 3 times -1/2 squared minus 36 times -1/2, right? That's... What do you got? 18.5? 18.5? That's what I got too. So that means as a point, it's -1/2, 18.5. 18.5. You could put -0.5. Now, Myra, I heard you. What did you say about your calculator? Can't you just what? Sure. To evaluate it? Yeah. But that plugging a value into function is a skill that's way, way back, right? So however you do it now is fine. Okay? Are there any questions on this? I think we've answered everything. What I would like to do, though, is what I've done before and try and just look at the graph of this real quick. Myra, you bring in a very good kind of question, something that we can talk about. Technology is to a point where it can do a lot of calculus for us, So there's this big debate, why teach all this stuff if, you can just have a computer answer all these questions? And that's a really good argument, What do you all think? This is the graph right here. We've had some, here we go. Let me try. Remember last time we did this? This sucked. Let's try it again. 10. 10. I don't know why it didn't work last time. What was our maximum? Was it 81 or something like that? So I'll make it 90. Okay. I think we can kind of tell from this, can't you? That our function, where is our function going up? All the way till we get to some value here, some x value, right? Then it goes down for a while, and then it comes back up. We can see that the local maximum occurred at, what did we get? Negative what? Where did the maximum occur? -3. Yes? And the minimum occurred where? At 2, right here. Where's our inflection point? Negative 1/2, 18. Right about here is where our inflection point is. Kind of matches up, right? To the left of that arrow, frown. To the right of the arrow, it's a smile. Yeah? Okay. Do you think with what I've given you, you can handle a quiz? You can try at least? Well, I'm going to give you 2 problems. The first one is going to be a nice polynomial. The second, well, I'm going to give you 3. The first one's going to be a polynomial. The second one's going to be a rational function. The third one's going to be a trig function. So I want you to do at least 2 of these, all right? I'm only giving you 3 in case I've got to go run and meet with the math department real quick because I was supposed to go to a meeting this morning and I missed it. And so I'm going to run over there, let y'all do an in-class quiz. It's supposed to be like 15, 20 minutes. I'll be back, okay? Help each other out, though. I mean, this is an opportunity to get 100 as long as you can make it happen. Okay, so let's just put on here quiz. You will turn this in. Put today's date. All right, the first problem. It's the same instructions as the ones we just did, okay? F of x equals 4x cubed plus 3x squared minus 6x plus 1. Second one, f of x equals x over x squared plus 1. And the third one, f of x equals sine x plus cosine x on the interval 0 to pi. Now let me say something about number 3. On number 3, I'm not asking you for absolute max and min. I'm asking you for all the local maximums and minimums. All right? So follow the process that I just went through today for all of those problems. Don't revert back to what we did in 4.1 for number 3. Okay? You think you can handle that? All right. Good luck. If you finish before I'm back, just take a break. All right. I wanted to show you on the quiz number 2 that everyone's working on, that x over x squared plus 1. This is the graph of that function. And I just wanted to point out, first of all, the max and min. You have one max right here. It happens, it looks like at 1, what, 1/2? At 1, 1/2. That's your local max. And then, let's see, the next one was at -1, -1/2. So you can tell by the graph, that's your local min and local max, right? And then you should have 3 inflection points. There's one right here. You can't really tell, but this is a frown turning into a smile. Smile, smile, smile. Then comes frown, frown, and then this is the bottom part of a smile. So again, just to verify what the algebra returns to us. Okay? All right, I want to do another problem like this. I'm going to work pretty quick through it, though. Let's look at, where is it? F of x equals cosine squared x minus 2 sine x on the interval 2 pi, or 0 to pi. So this will help you with that third quiz problem. All right, first derivative is -2 cosine x sine x minus 2 cosine x. So what I had to do here Remember, on cosine squared x, that's chain rule, isn't it? Right? Something squared. What's the derivative of something squared? 2 times that something times the derivative of something which was negative sine x. Right? So the yellow highlighted, the derivative of the yellow is the red, right? And then I just move the negative out front. And then the derivative of negative 2 sine x is negative 2 cosine x. So any questions on that? Good? All right. So what are you supposed to do with this now? Set it to 0, right? So when I take the derivative and figure out where it's 0, I take negative 2 cosine x sine x minus 2 cosine x. I set it to 0. I can factor out what? Negative 2 cosine x, and be left with sine x plus 1 equals 0. And then set each of these equal to 0. And what about the negative 2 out front? I can just, basically I could divide everything through. Like I could divide everything by negative 2 right now, and the negative 2 would go away, wouldn't it? So I don't need it. So I have two equations. Cosine x equals 0 and sine x plus 1 equals 0. Because it's being multiplied, so I can divide everything by negative 2. And when I divide the other side by negative 2, I still get 0. So I have two equations here. Cosine x equals 0, and the other one, if I move the 1 over, sine x equals negative 1. So I have to determine when is cosine 0, and then when is sine negative 1. So I'm going to go to my unit circle. Cosine is which coordinate? X coordinate. So when I'm trying to figure out when's cosine x 0, I'm saying where's my x coordinate 0 on the unit circle? Pi over 2 and 3 pi over 2. So for this first equation right here, I get x equals pi over 2 and 3 pi over 2. And I don't go any further than that because the interval we're looking at is 0 to 2 pi, right? 0 to 2 pi. When is sine x negative 1? Sine is the y coordinate, right? When is it? Down here, right? That's when your y coordinate's negative 1. But that's also 3 pi over 2, isn't it? Which I already had. Didn't I already have 3 pi over 2? Okay. So once you get the points, we now need to look at when the derivative is undefined or doesn't exist. What can you say about that derivative? Is it well behaved? Is that a well-behaved function? Negative 2 cosine x sine x minus 2 cosine x. Well, aren't the sine and cosine function continuous functions? And when you multiply them, they're still continuous. And when you add and subtract, still continuous. So there's no issues with that. So that's a nice function. This is not going to be something we worry about. We are going to run into that issue eventually today. So now I'm going to draw a number line. I'm going to put on it pi over 2 and 3 pi over 2. And then I'm going to test points. Now keep in mind, I'm only supposed to be looking between what? 0 and 2 pi. So make sure that your test points don't go past those extremes. Someone give me a test point to the left of pi over 2. Pi over 4. Good. How about something between pi over 2 and 3 pi over 2? Pi. And then something bigger than 3 pi over 2? What? I'm sorry, I didn't hear you. 11 pi, oh, what the hell? 11 pi over 6. Do y'all agree? Those all work. Where do you plug those in? To the derivative, right? So I want f prime of pi over 4. That means I need to go up. Where's my derivative? I forgot. There it is. So negative 2 cosine pi over 4 times sine pi over 4 minus 2, what was it? Cosine pi over 4? Everyone understand what I'm doing? All right, what's cosine of pi over 4? Pi over 4? Root 2 over 2. What's sine of pi over 4? Root 2 over 2. Minus 2 times cosine of pi over 4 is root 2 over 2. So I get negative, let me see. What do these first 3 multiply out to be here? Isn't the root 2 and root 2 multiply to be a 2? And then times negative 2? Gives you negative 4 over 2? Or over 4? Over 4. Negative 4 over 4? It's going to be negative 1, right? Minus, on the other one, don't the 2's cancel? Just comes minus root 2. Is that answer positive or negative? Negative 1, take away root 2. That's a negative number, isn't it? So this is less than 0. What does it tell me about my function? It's going down. F is going down over here. Now you have to do the same thing for pi. Y'all get what's happening or not? Okay, let's just figure out what f prime of pi is. Negative 2, what's cosine pi? Negative 1, what's sine pi? 0. Minus 2 times what's cosine pi? Negative 1. This turns out to be 2. That's bigger than 0. So my function is going up over here. Now I'm not going to test the last one, 11 pi over 6. You could do that yourself. What you would determine, I think, hold on. Let's see. In the fourth quadrant, both sine and cosine are both negative. So I'll have a negative 2 times a negative times a negative. That'll be negative. And then negative, shit, that's positive. So I don't know for sure what's going to happen. Did I say fourth quadrant? Yeah. 11 pi over 6 is in the fourth quadrant. Oh, no. Cosine. That's right. Cosine's positive. So that would be positive, negative, negative. So that would be positive and negative. I still have to. I might not be able to avoid it. I might have to plug this in. 11 pi over 6. Damn it. Okay, negative 2. What's cosine of pi over 11 pi over 6? Root 3 over 2. What is sine of 11 pi over 6? Negative 1/2. Minus 2 times cosine of that is root 3 over 2. Okay. I get some of these 2's to cancel. I get a positive root 3 over 2 minus a root 3. Oh, whoa. So is it positive or negative? Negative. So it goes down over here. What's that? Root 3 minus the root 3 what? Are you asking me a question or are you pointing something out to someone else? But there were two negatives, weren't there? There was this negative and this negative that made it positive. Is that what you were also saying? Or you're just talking about this right here? Well, you can't put those together because they don't have the same denominator. So you'd have to get a common denominator before you could put them together. But think about, I mean, you can just look at it this way. This is an apple, okay? Green apple. Half of an apple. Take away a whole apple. Right? I mean, it's oh, they're not. Okay, so you're okay with that then? All right. I just want to make sure everyone's on the same page as why we have a negative there. Now, you might be saying to yourself, hey, look, all these problems we've done so far, it's always switched, right? It went down, then up, then down. So if I just find the first one, I know it'll switch. That's not the case. You always have to test. All right? Now, let's just look at this second derivative. It doesn't look like fun to me. I'm going to do the second derivative right up here just because I can see it on one page. All right. I'm trying to take the derivative of this thing here in green. I have a product rule right there. Right? So what's the derivative of negative 2 cosine x? Negative 2 times negative sine x, right? Which is just then 2 sine x times the second function, sine x again, plus what's the derivative of sine x? Cosine x times negative 2 cosine x, right? I'm going to run out of room. Do y'all see that as a product rule in that first one? Am I done with the product rule or not? I mean, I'm done with the product rule, right? But I'm not done with the derivative. I need to do what now? What's missing? Plus 2 sine x. What is that? That's the derivative of what? The minus 2 cosine x. Elias, yes? This equals 2 sine squared x minus 2 cosine squared x plus 2 sine x. Yay or nay? Well, unfortunately, we have to set that to 0, don't we? So let's get to a new page. So f double prime of x was 2 sine squared x minus 2 cosine squared x. Was it plus? Yeah, it was plus 2 sine x. Now, when is my second derivative equal to 0? And when is it undefined or doesn't exist? I'm going to scrap that doesn't exist because it's a bunch of trig functions, so I don't need to worry about it. Well, it's a bunch of sine and cosine functions. Any idea on how to set this one equal to 0? Take out a 2? All right. It's fine with me. You take out a 2 and divide everything by 2, right? So I can just go 2's are gone. Now what? Good question, right? It would be nice if that was sine squared x plus cosine squared x, wouldn't it be? Because then it would just be 1, wouldn't it? That'd be too easy. So I look at this and I realize I've got a sine squared x and I have a sine x, right? And then a cosine squared x. But don't we have an identity? What does the half angle say? For sine squared x? Yes, you could do that. You'll be doubling an angle, won't you? When you do that, you create a 2x inside the trig function, don't you? Like, say again what you were asking. Okay, so which one? The cosine squared one? Just read the one that you were, because I want to explain why you wouldn't. That's what I'm saying. It becomes a cosine 2x. There's a 2x inside the cosine when you use that identity. And none of your other trig functions have a 2x inside of them. Right? Your sine squared doesn't have a 2x. Your sine x doesn't. How about this? I'm just going to go for something here. What did I do? Replaced cosine squared x with the Pythagorean identity. I took the identity sine squared x plus cosine squared x equals 1, and I solved for cosine squared x, which means you move the sine squared to the other side of the equation. And what does that allow me to get here? And why would I do that? What am I going to gain by doing this? 2 sine squared x, right? Plus sine x plus 1 equals 0. What type of equation is this? If you squint your eyes hard enough, that's a quadratic equation we'd say a quadratic equation in sine. In other words, if I look at the sine x as being like a variable, I have like 2u squared plus u plus 1. It should be minus, it should be minus 1. Sorry, I forgot the sign on that. Y'all see what I'm saying? That kind of looks like 2u squared plus u minus 1 equals 0. It's like a quadratic form. So it can factor to be 2 sine x times sine x. Let's see here. Plus 1 here and minus 1 there. Does that work? Is that the correct factoring of that? Yes. So that's pre-cal stuff. Trigonometric equations. Set them both equal to 0. 2 sine x minus 1 equals 0. Sine x plus 1 equals 0. Sine x equals 1/2. Sine x equals negative 1. So now I'm going to go to my unit circle and ask myself some questions. At what angle is sine x equal to 1/2? So when is the y coordinate 1/2? Those two spots, right? Pi over 6 and 5 pi over 6. Where is the y coordinate negative 1? 3 pi over 2, right? So we set up a number line. We put this in order. Pi over 6. 5 pi over 6. And 3 pi over 2. Whoa, whoa. Remember that we are looking between 0 and 2 pi. So our test points need to be in there also. I'm supposed to plug these into the second derivative, right? Does anyone have any questions? I know I'm moving kind of quick through this. Anyone have any questions? No? It's a lot, right? Now, I have some options here. I'm supposed to pick an angle to the left of pi over 6. That means I need to pick an angle somewhere in here. And we don't really know any other angles like off the top of our head smaller than pi over 6. Like our unit circle, the smallest one is pi over 6. So let's think this through instead. Let's try and think it through. I don't know if this is going to work. I'm just going to pick a point over here. How about, and I don't think there's any way we're going to be able to do it without plugging in. Let's just try this angle right here. Let's just try this without plugging in. I'm going to plug it in to this. I'm boxing it right now. I'm going to plug it into this because that's the second derivative factored, isn't it? Let me just plug in there real quick. If I say sine of whatever that green dot is that bigger than a half or smaller than a half? Because what was sine here at this blue dot? What was sine there? It was a half, right? So if it's below that, the y coordinate is smaller, right? So what would 2 times a number smaller than a half be? Bigger than 1, wouldn't it? Is this too much? Am I pushing too far here? I think I might be. Y'all give me no indication of where y'all are at all. Silence, yeah, silence means you all understand, right? The y coordinate, look. Didn't we say the y coordinate right here was 1/2? On the right side of that circle is 1/2, wasn't it? So this, if we pick an angle smaller, that number is going to be smaller than a half, isn't it? Let's say like 1/3. I'm just giving an example. So if I then come over here and I plug in right here, 2 times 1/3 would be 2/3, right? Subtract 1 from that and you get negative, wouldn't you? So it will be a negative number. Okay? It's a negative number. Now, what's sine of x here? We said it would be maybe 1/3, smaller than a half. Plus 1 would be 1/3 plus 1. It's a positive number. So what is a negative number times a positive number? Negative. You see, I'm doing that without even plugging anything in, technically. I can tell you it's going to be negative. Now, what that means is it's concave down over here. Now, what would you do if you couldn't do this? Just get your calculator out. Make sure you're in degree or radian mode, whichever you want, and plug into this the second derivative, which is up here. So maybe you put in degree mode and you plug in like 10 degrees, something smaller than 30. Okay, I need a number between pi over 6 and 5 pi over 6. There's a good one right here. Right at the top. Pi over 2. Right? So what is sine of pi over 2? 1. So plug into that same one that I had boxed there. What's 2 times 1? 2 minus 1 is 1. So that first box over here, this first thing is a 1, right? That's a 1. And then plug in over here, what's this going to be? 2. So 1 times 2 is 2. So it's positive. What does that mean? Concave up. Then it's going to go down. And then it's going to go up. I'm not showing those. I'm just leaving it to you. So where are the intervals where I'm... Did we even do that earlier? You could do all the intervals, though, now? I mean, at this point, all the information's there, right? All you have to do is say, it's concave up between pi over 6 and 5 pi over 6, unioned 3 pi over 2 to 2 pi, concave down from 0 to pi over 6, union 5 pi over 6 to 3 pi over 2. Do we have inflection points? Where are they? Pi over 6, 5 pi over 6, 3 pi over 2, right? Okay. I wanted to do that problem just to show you the sort of trig stuff you can run into. What do we have here? Cosine x squared minus 2 sine x there's the function. What is 2 times pi? About what? 6.2, 6 point something, right? So if you just look at this function, just between 0 and 2 pi, which is about out here somewhere, we had a local max, or sorry, a local minimum where? What was our answer for local minimum? Pi over 2, look at this. Pi over 2, there it is, lowest point. Where do we have a max? 3 pi over 2, here it is, right? Okay, where did we have inflection points? Pi over 6, right here is an inflection point. 5 pi over 6, there's the other inflection point. Where was the other one? Where? 3 pi over 2, right here. Oh, you know what? Hold on a second. We're concave down, concave down. Oh, we went from frown to frown. You know how I just put this right here? This is wrong. Look, I made a mistake. You can mark it. Look, right here. This should not have switched. It would have been frown, frown. Then 3 pi over 2 is not a point of inflection. So you can feel free to do something like this at home. Graph it, see if it matches your answers, you know, or even on a test. All right, we're going to put this, I think we're going to put this behind us. Now we're going to put it behind us, but in no way are we done. We're just moving to the next section, which is basically this with a little more added onto it. Yes. Yes. Yep. Can you what? Well, again, here's the idea. Look, if we were all using computers, if this class was everyone has to have the TI whatever, I would teach this class, and a lot of this you wouldn't do by hand. You know. Yes, that's what this is about. Yeah, it's about the algebra of the derivative and all that stuff. That's what this is about. So, unfortunately, that's the way the class is. And if you're going to go on and do more math, at some point your calculator will not be able to do it. It's not going to be there. All right, so you've got to be good at algebra. What about this curve sketching? That's the next section. Ooh. So before graphing calculators, right? There had to be a way to graph functions. Computers can do them now, right? But before that, how is it done? Well, there's a set of steps, a procedure, so to speak. And here it is. It's going to be a 9-step process for us. That's what I'm going to go through. And let's just go through them first. We're going to be given a function. We're going to find its domain. We're going to find the x and y intercepts. We're going to check for symmetry. We're going to find any asymptotes. Now here's where the calculus starts. Determine if the intervals where the function is increasing, decreasing, and constant. Find local maximum, minimum values and where they occur. Determine where we're concave up and concave down. Also determine inflection points. Make a table, sketch the curve. So basically steps 5, 6, and 7 are what we were just doing. But now we've added on all this other stuff. This is a real pain in the ass part of this class right here, okay? But if you ask a lot of Cal 1 instructors, they say, what are the main things you want a student to be able to do at the end of Cal 1? Related rate problems, the ones we were doing. Balloon is filling up at a constant, rate of blah, blah, blah. Okay, curve sketching, optimization, which is the section after this. All right, well, let's do this. I'm going to follow this procedure right here. I would like for us to take this function, f of x equals x over x squared minus 9. And I'd like to sketch it using calculus. Basically saying, doing what we're doing in this class, all right? The first step, you should have your notes printed out for chapter 4, so I'm going off of that. First step is domain, right? What is the domain of this function? Everything except negative 3 and positive 3, right? Those are the only two. So the way we say that, negative infinity to negative 3, union, negative 3 to 3, union, 3 to infinity. That's the interval way of notating the domain. Second step, x-intercepts. How do you find the x-intercepts of a function? You take it and you set it to 0. But our function is a fraction, so you only have to set what to 0? The top. And if you set x equal to 0, holy crap, it's already there. X is 0. That's your x-intercept, right? How do you find y-intercepts for a function? You plug in 0 for x, don't you? You replace x with 0, and you actually get 0 again. So the x and y-intercept are actually the same point, aren't they? It's the origin. I would ask you if you have any questions, but I know you're not going to answer me, so I'll just carry on. Check for symmetry. I'm going to skip this. I'm not going to ask you to check for symmetry, because to check for symmetry means that you have to understand what even functions and odd functions are, and we could spend a lot of time doing that, and it's something you're supposed to know, but I know a lot of students don't. It's okay. We can live without it. All right? We can live without it. It just can speed things up later, but we'll skip. Okay, find asymptotes. What type of asymptotes are there? There's two that we usually study in college algebra. Vertical and horizontal. Okay, where do vertical asymptotes occur? They're vertical dotted lines, right? But where do they occur? Algebraically, in our function, here is our function. I'll put it back up here. Don't vertical asymptotes occur whenever our denominator is 0? Right? Where our denominator is 0. So 3 and negative 3, right? So 3 and negative 3. Those were the points that weren't in our domain, right? But what we need to recognize is that at those points, we will have vertical asymptotes. How about horizontal asymptotes? Anybody remember how to find the horizontal asymptote of a function? What does it mean, horizontal asymptote? Isn't it what's happening as you go out the sides? Isn't it? Yes? We're asking ourselves, what is the function doing as you go out to the sides forever? Exactly. You're asking this question. What is the limit as x goes to infinity of the function? That's what you're asking. Tell me what's happening in the function as I let x go out forever to the right. So what is the limit as x goes to infinity of x over x squared minus 9? So let x go to infinity, everyone. What do you get? What form limit is this? What form do we have? Infinity over infinity. Good. What do you do when you see infinity over infinity? L'Hopital. Good. Take L'Hopital's rule here. What's the derivative of the top? 1. What's derivative of the bottom? 2x. Now, let x go to infinity again. What do you get? Fixed over infinity. Where does that go? 0. Right? So you have a horizontal asymptote of 0. That means as you go out to the sides, this function is headed to 0, which is the x-axis, isn't it? Isn't 0 the x-axis? I'll draw a little picture next to this. We're saying as you go out to the right, our function is headed to 0. That's like the x-axis, isn't it? Like that. Now, it might be coming up from the bottom also. It's just going to depend later when we draw it. But I can guarantee you that's what's happening. What if we went to negative infinity instead of positive infinity? Wouldn't we still get infinity over infinity? We do L'Hopital, and then you get fixed over negative infinity. That would still go to 0. So out the left side, it's also going to 0. All right, so for asymptotes, for horizontal asymptotes, you actually have to take a limit. Step 5. Determine where, I want to know where f is going up, where f is going down, where f might be constant. Here's what I use for constant, just a flat arrow like that. So when we talk about a function and where it goes up and down, what do you have to do? Take a derivative, right? So I'm going to start a new page. I'll start this over again. So I need to take a derivative. The derivative of this function is 1 times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now that's very similar to the one you did in class just a second ago, isn't it? All right, let's go ahead and clean that up. What do we have here? Is that negative x squared minus 9 over x squared minus 9 squared? Do y'all agree with that? Yeah. Can't simplify that, right? Can't cancel the x squared minus 9 because they're both negative, unfortunately. Now we have to ask two questions, remember? Where is that 0 and where is that possibly undefined? So where is it 0? Well, when is a fraction ever equal to 0? Only when the numerator? So don't I just have to look at this? Just the numerator to 0? Go ahead and move the 9 over. What can you tell me already? Right here, what can you tell me? You can do it the other way around too. You can put x squared equals negative 9. No solution, right? No real solution. The only way that you can square a number and get a negative is if you use the imaginary unit. The numerator is what? Did I write the problem down wrong? What was the original function? Okay, the original function was f of x equals x over x squared minus 9, right? To go from here to here, I distributed the 1 through, which doesn't change anything. It's just x squared minus 9. And then I did these two together right here, which gives me negative, or that gives me 2x squared. So I have minus 2x squared. And then, why don't y'all ask when I ask you? I know, but if you see me do something you don't get it, I want to help. Well, then tell me to slow down, because I am happy to slow down. Okay, so we have no solution for this, right? But I still need to look at the fact that the second derivative could be undefined. Now, this is the first time we actually have an issue, don't we? We have an issue where? When the denominator could possibly be 0. And when is that denominator 0? 3 and negative 3 again. So I am going to get a number line out of this, right? The only two numbers that are going to go on my number line are 3 and negative 3. And I'm going to test some points. This is kind of interesting. Can anybody tell me what I'm going to get with those test points? Doesn't matter what test point I plug in. What can you tell me about the numerator? Negative x squared minus 9. What is that always going to be? Negative number, right? Because when you square a number, right? When I square a number right here, it's going to be positive no matter what. But then I put a negative in front of it. And then minus 9 is still negative. Now what about the denominator? Doesn't matter what happens with x squared minus 9, right? Because what are you going to do after you do the x squared minus 9? Square it. So you're going to have a negative on the top and a positive on the bottom. Always. Unless you plug in 3 or negative 3. But we're not plugging in 3 or negative 3. So doesn't that mean my original function is always decreasing? Does anybody have any questions? Yes. I set for the part right here, the f prime undefined part, on the other side, I set the numerator equal to 0. Yes. Yes. I did this right here, went with this. Because the only time a fraction, well, I actually am setting the entire thing to 0. But the only time a fraction can be 0 is if the numerator is 0. So the function is always decreasing, correct? All right. What would be our next step? I mean, we could determine where it's going down, where it's going up, right? Let's do that real quick. Where is the function decreasing? Someone tell me where it's decreasing. Everywhere? Be careful though. Yeah, because remember our original function wasn't defined at -3 and 3? So our function isn't, I mean, it's everywhere the function exists, except for the asymptotes. So that's where the function's going down. Where is the function going up? What's that? It's not ever going up. So how do I represent that? Null set. Good. I was hoping someone would get that. Null set. Empty set. Yep. Does anybody play what's that online poker on the phone? What's that called? Shit. On Android. God dang it. Well, I don't even know what it's called. Anyway, my name on that poker is Null Set. That's my poker name. All right. Do we have any local max, local min? Do you ever see a change from decrease to increase? Okay. Now look, I know it's been a long day. I know y'all are ready for the end of the summer to come, but let me just put something here because I need you to pay attention to this. Let's just say in blue here that this went up. Okay, let's just say for the sake of argument here and just demonstration. Would we have a local minimum and a local maximum? No, we wouldn't. Exactly. Why not? That's right. Because this is not, remember, the first derivative test said, right, we have to go from down to up, but the function has to be defined there, right? Our function is asymptotic there, so you can't have it go to a lowest point and then a highest, I mean, like go down and go back up. Because that's right. You're never going to have a local max or min at a place where your function's undefined. That's why it's so critical for us to pay attention and just be like, I don't want you to just be like, oh, I see down and up, oh, automatic, it is the minimum. You know, I mean, you got to think through the entire problem and like understand what's going on. Well, it's going to look like this. It's going to go like this and then like this. And we're going to have an asymptote like that. So to the left, it's, oh, well, you know what? I would have to draw it like this. This is the way, if I'm drawing it the blue, okay, the hypothetical situation, the left side of that asymptote, we're going down. The right side, we're coming up. That is not a local minimum. But the only way we'd know that is to remember that -3 is where you have an asymptote. -3, the function's not defined. Pardon me? Well, there's only one vertical asymptote, and from one side it goes down, and the other side it goes down towards it also. They both explode negatively, I guess you could say. They get very large negative as they approach that. But that was just Yes, there would be another drawing. Yeah, if you wanted me to draw both of these, I would have something like this. This would be doing this. This would be doing this. Over here it would be doing this, and then over here it would be doing this. That would be, decreasing, increasing, decreasing. All right, what do I need? We're done with that? No local min. No local max. Yep, now step 6, right? Oh, that is step 6. Step 7. Determine all the intervals where we're concave up and concave down. What do you need for this then? You need the second derivative. So let me put the derivative back up here. It was negative x squared minus 9 over x squared plus 9 squared. The second derivative using the... Oh, thank you. That would have been hell later. The second derivative using quotient rule is negative 2x times x squared minus 9 squared minus the derivative of the bottom. Who wants to volunteer the derivative of the bottom? 2 x squared minus 9 times 2x times negative x squared minus 9 all over x squared minus 9 squared, which is fourth. Whew. Now this is where I had come into the class to see where y'all were on this, and a lot of people had gotten hung up on the second derivative because they tried expanding all that out. Whenever you do a quotient rule like this, and you have this and you're trying to break it up and factor, always try and look for common factors here. Like I have an x squared minus 9 here, x squared minus 9 here. What else do I have common in both of these? I have a 2 and an x and a negative. So I'm going to pull out of the numerator, I'm going to pull a negative 2x times x squared minus 9 out of both terms. Now remember, the terms are separated right in here because there's your subtraction. So this is a first term over here, second term's over here. So f double prime of x equals negative 2x times x squared minus 9. That came out, right? That's what I'm pulling out. And now I'm going to use a big bracket. What would be left in the first term if I pulled out a negative 2x times x squared minus 9? Just x squared minus 9. Because I pulled one of them out, right? There were two of them right here. And I pulled one out, which leaves one still there. The minus 2x is gone, but there's still an x squared minus 9 there. That okay? What's left if I pull a negative 2x times x squared minus 9 out of the second one? 2. I'm pulling a negative, right? So plus 2 is still there, and then what else is still there? The negative x squared minus 9. Remember that 2x came out. It was common in both, right? It's kind of like if you took this big clump right here and you distribute it to this and then distribute it to this, you would get back what you had above. All of this over what? X squared minus 9. to the 4th. Help me clean up the inside here, inside that big bracket. What does that big bracket become when you clean it up? Negative x squared minus 27. Good. All over x squared minus 9 to the 4th. Does anybody have a question? Anybody see anything else we can do? Yes, you can. You can cancel this one with one of those to make it a cubed. And so we sit here with negative 2x. I'll get rid of the brackets. Minus x squared minus 27 over the x squared minus 9 cubed now. That is the second derivative. And we'd like to know where this is undefined and where it's 0, right? I'm going to move to another page. F double prime x equals negative 2x times negative x minus 27. No, x squared, right? Negative x squared minus 27? Or negative 2x squared? Just negative x squared? Okay. X squared minus 9 cubed. Okay, where is this thing 0? Only the numerator, right? So negative 2x, negative x squared minus 27 equals 0. I can divide both sides by 2, negative 2. I get two things. X equals 0 is one equation. Negative x squared minus 27 equals 0. So x equals 0 is one answer, right? What about the other equation? Move the x squared over. X squared equals negative 27. No solution. Where's the second derivative undefined or does not exist? Do you have any issues with the second derivative? Same thing as before, positive and negative 3. So we still have an issue there that causes that thing to go crazy. Are we ready for a number line? What goes on this number line? 0, 3, negative 3. You can see why you're probably only going to have like one of these on your test. On your final. This is what we would consider to be like a capstone problem in this class. If you can do this problem, you know, you're taking first, second derivatives, you're using algebra. I mean, there's a lot of stuff in this problem. So it's the litmus test Y'all know what I mean by that? I'm going to pick -4, -1, 1, and 4. And where am I plugging those in? Second derivative, right? Second derivative. Let's plug in -4. I'm going to do it up here so we can see it. Oops. What is f double prime of -4? We get, see, -4 times 2, it's going to be 8. What can you tell me about the negative x squared minus 27? What will that always be? A negative number. So I'm just going to put negative in there because I really don't care. And then what about the bottom? When we plug in -4, you get -4 squared is 16. Take away 9. Positive, and cube, positive. So we get a positive on bottom. So that's negative, right? What does that tell us about our function? It's, be careful, concave down. What about -1? What's f double prime of -1? Well, let's see, I don't know. It'll be negative, so 2 on top, -1 on the bottom. No, the bottom's negative this time. So you get a negative over negative. So positive, so it's concave up. Plug in 1, you get negative on top, and you get negative on the bottom. Ooh, concave up again. Wait, no, hold on. 1 on the top. I'm going too fast. 1 on top is negative. 1 on the bottom is negative. Square. It's positive, right? What about on -1? Let me go back to -1. It was -2 times -1. Then we knew that was a negative. All over -1 squared is 1. Take away 9. So that's negative on the bottom. Shouldn't the top have been positive? Is that what we said it was? Positive. No, it's negative. Yeah, put in your... That's really the point here, is that we can sit here and go through this and try and do it quickly, but at the end of the day, you just have to plug numbers into a function, right? And take your time through it and get it right. Let me just do something real quick. I know that's negative, that's positive. I know that's x plus 3, x minus 3. So if I plug in -1, I get negative. So that's positive. If I plug in 1, I get 1. So 1 should be negative, right? This one should be negative. And then plug in 4. 4. Positive. You need to practice plugging those in yourself, okay? So what does this tell us? Where's our function concave down? Did anybody get something different than that? Because I really went quick through that. I'm not really paying too much attention. Anyone try it? Get something different? No? Where are we concave down? -infinity to -3, union 0 to 3, right? That's what I'm talking about here. Where are we concave up? -3 to 0, union 3 to infinity. How about inflection points? What do y'all think about inflection points? Only 0. Only 0. Why not -3 and 3? They're not in your domain. Those are your asymptotes. So only 0 gives you an inflection point. And then we'd say 0, and then you have to plug that into the original function. What do you get if you plug 0 into the original function? you get 0. So the origin is an inflection point. All right. We have done steps 1 through 7. Now it's time to do step 8. Make a table. So look, if this is your page, I would start maybe a new page, all right? Oh, shit. Okay, if this is your page, starting in the first half, we're going to do the top half is going to be a table, and then the bottom half is going to be a drawing, okay? So everyone make sure you have a full page to work with here. Okay, what I'd like for you to do now, this is make the table. And the way the table is going to work is as follows. Just draw a number line. I want you to put first on this number line all of the places where your first derivative was 0 and all the places where your first derivative was undefined. So where was our first derivative 0? Nope, that's where it was undefined, right? There was no solution for where it was 0, so I'm not going to put anything. But where was it undefined? At -3 and 3, okay? So everything I got from the first derivative I'm going to put here. -3, +3. Now, go to your second derivative. Where was your second derivative 0, and where was it undefined? 0, right? And 3 and -3, right? Okay, so all you do to start this is draw out basically the critical numbers for both the first and second derivatives. Bless you. Now, above this, I'd like you to draw 1, 2, 3 lines, and then we're making a table here, like this. And then dotted lines coming straight up from those critical numbers, like this. Then on the left side of your table, I want you to write F prime, F double prime, and then F. So this is kind of a weird order that I just did that. I started with the first derivative, then second derivative. If you go from the bottom up, first derivative, second derivative, then F. Everyone with me? Okay, I'm going to look at this row right now, okay? Just so you know, that's what I'm looking at now. Go back to the number line that we had from the first derivative. And what were the arrows on that first derivative? They were all down everywhere, right? So what I'd like for you to do is draw arrows down, down, in each of the boxes of your table, down, down, down. Now, go to your second derivative number line and tell me what we had. It was down. Okay, so where was it down? From starting at the left side, it was down to the left of which number? -3, right? So it was down like this. Then it was up between -3 and 0. Then it was down. And then it was up. Do we agree with this? Okay. Now, this is the part that takes a little bit of thinking. The top row is going to be a frown or a smile, but not the entire frown and not the entire smile. It's like you have to cut the frown or smile right in half. Now think about this. I'm going to look right now at this one right here. Just look in here. What is the only way you can be a frown but be decreasing at the same time? Which side of the frown are you on? The right side of the frown, right? If I move from left to right, I'm going down, but at the same time I'm frowning. Agreed? Do you see how that couldn't be the left side of the frown? Because then you'd be going up. What is, now go to the next column. What's the only way to be going down a smile? The left side. So it looks like this. Then what's the only way to be going down a frown? Right again. And the only way to be going down a smile? Left side. See how that works? Now, a lot of textbooks, I've never seen a textbook do it this way. A lot of textbooks use what's called a sign chart. And they use like positives and negatives and things like that. And I remember when I was like, what? And so this is the way it made most sense to me. This is the way I'm presenting it to you. We basically are putting together the information about the first and second derivative to come up with a basic idea of what the function looks like. With me? Okay, now we are done with part 8. Now we're going to go to part 9. This is the very end of the problem. What I'm going to do is starting right below my table, I'm going to draw my x and y axis for my picture. And notice how I'm kind of just transposing that number line, -303, just down. Y'all see that? I'm lining everything up. Yeah? Or no? Okay. It's all lined up and even. Now what I'd like for us to do is go back to the very beginning of the problem and start going through our information again. We know the domain of the function was -infinity to -3, then -3 to 3, then 3 to infinity, right? So we know where we should have a graph. Where's the x and y intercepts? No, the x and y intercepts. 0, 0, right? So it's time for me to start drawing my function. I'm actually going to draw this dot at the origin. That black dot lives on my function. Okay? Check for symmetry was step 3. We skipped it. Step 4 was find asymptotes. What did we find for asymptotes? -3 and 3 were vertical asymptotes, right? So I'm going to draw them as vertical dotted lines. They are not part of my graph, right? They are just these barriers that force my function to go up or down when I get to them, right? I can't cross vertical asymptotes. I got to go up or down when I get to those, when I draw my function. What about horizontal asymptotes? Where did we say we went towards the ends? Remember when we took that limit? It went to 0, didn't it? So I'm going to draw on the right side a dotted red line going out the x-axis. Same thing with the left side. Next thing. I've got to figure out where I have any other information about this graph. Right now, this is all I've got. I know that over here in this region, right? Over here, I know my graph must look like this little side of this frown, right? And I know in this region here, my graph's got to look like that part of the smile. And I know that in this region here, it's got to look like that part of the frown, right? You get it? What could help guide me to draw the rest of it is by having just one point in each of those regions and plotting them so I know where the function is. So what I'm going to do, I'm just going to leave those colors up there. I'm just going to pick a point, any point I want over here, any point I want in here, any point I want here, any point I want here, and I'm going to plug those points into the original function. So let's try -4. Is that a good one? Put -4 into the original function. What do you get? -4 over 4 squared is 16, so 7. It's a negative number, isn't it? -4/7. So you could get that as a decimal. It's a little less than a half or a little more than a half? I'm labeling my y-axis -1 there. Over here, it would be somewhere in this neighborhood. I'm going to put it in black. It'd be somewhere around here, right? That's close enough? Now plug in -1. What would you get if you plug in -1? -1 over -8, right? Which would be 1/8. So over here at -1, wouldn't I be up just a little bit like this? What happens if you plug 1 into the function? -1/8, so now you're down here. And what would happen if you plug in 4? +4/7, right? So you'd be here. All right, we're ready. Let's draw it. So I've got my table above this, right? What I know is that at this black dot, I've got to go towards this asymptote, and I've got to go down like this, right? That's basically it, but I'm going to draw it a little better than that. That's kind of crappy. I know that the entire time I draw it, it must look like the right side of a frown. Does that look like the right side of a frown, pretty much? What about from the origin out to the left, out this way, right? I've got to look like the left side of a smile. So I'm going to connect those dots. It's got to go like this and then go through that. Damn it. Go through that and then go up. And the vertical asymptote forces it up, right? The right side, coming out the right side, must look like the right side of a frown. So it looks like this. And then when I go over to the dot in the fourth little region over there, or third region on the right, it's got to look like the left side of a smile. So it's got to go up. And then it's got to come down towards the... Yes. That's a good question. Horizontal asymptotes do not block your function. All they do is tell you what happens at the ends. A lot of times I'll see tutors do this, like in tutoring lab. When they get a horizontal asymptote, they'll draw a dotted line all the way across, and that makes students think you can't cross them. Horizontals you can cross. Verticals you cannot cross. All right? So it's fine. Whatever's happening in the middle of the function doesn't matter. It's only at the edges you have to go towards your horizontal. So that's a lot of work, right? I mean, that is a friggin' tremendous amount of work for that rational function. But the idea is what I want you to understand, that you can take pretty much any function, and as long as you can do this process, you can sketch it. Oh my gosh, we're out of time. Well, yes. I know, sorry to disappoint you, Frank. Our homework's going to change a little bit here, so let me run back up to this. Was it that bad, Frank? I can handle honesty. Is it the material, or is just this class? Okay. This is the only thing you need to work on for next time. And as you probably are aware of now, that's a lot of frickin' work right there. Because 4.4 is what we just did, that problem we just did right now. That's 4 problems like that. And the derivatives on those are nightmares. So you should try and tackle, if I were to be sitting back and saying, what am I going to focus the next 48 hours on for homework? Like, where would I gain the most putting my energy? It would be going straight to 4.4 and doing 11, 19, 22, and 23, because those incorporate the skills from 4.3, right? You have to do the stuff from 4.3 to do those problems in 4.4. So that's where I would start. For next time, the watching of the videos, I'd like for you to, of course, watch 4.6, watch 4.7, but include with this 4.5 because I didn't get a chance to cover 4.5. Adios. If you have a question about your test or anything like that, feel free to... Oh,